Thank you. So today I want to talk about kind of two things at the same time. So on one hand, I want to talk about kind of principle-based approaches to physics versus model construction-based approaches, and especially in the context like interdisciplinary areas. And as a kind of case study, I'll use kind of debates around the nature of the gravitational field to illustrate these two approaches. Good. So, so principle versus model-based approaches, the example of quantum gravity. So there's, I guess, one of the main questions which have been occupying people for the past 6 years is how to quantize the gravitational field. So we have like string theory as an example, loop quantum gravity as another proposal. Okay, but then, I mean, why are people trying to quantize the gravitational field? Okay, let's take a step back. Okay, so say they want to unify quantum theory and general relativity. Okay, why do we want to unify quantum theory and general relativity? We want to describe quantum matter interacting gravitationally. And here I mean in the context where the quantum matter is back reacting on space-time. Okay, so we know just like a quantum particle in a kind of classical field, right? How that works, gravitational field, like the Earth and the test particle that Czazlav showed. But the case where there's back reaction, so the Earth in a superposition, this other scenario, these are the regimes why people kind of want to quantize the gravitational field. Okay, but does this actually require quantizing gravity? Oops, okay. Up. So, yeah, my claim is a priori, not necessarily. Right? I mean, there's not. It might be the case. You can just kind of think that we could have classical gravity and quantum matter, and that might be possible. So the first step people would do is if I kind of claim that, okay, maybe it's possible to have classical gravity and quantum matter, is to construct a model. So this is the model-based approach. So I take general relativity, okay, and then, for instance, instead of T mu nu, I now have an expectation value. Okay, so T mu nu hat is a quantum operator. It's expectation value on a state. And I have this so-called semi-classical Einstein's equation. So this is a model of classical gravity interacting with quantum matter. So you do this, then you work some stuff out, and you find that the kind of matter degrees of freedom follow what's called the Schrödinger-Newton equation. Okay? It's a nonlinear Schrödinger equation. Okay, so we have this nonlinear Schrödinger equation, so then you've built your model, and then you go, oh, wait a minute. You see stuff like violation of the uncertainty principle, and then if you try and talk about multiple systems, you see the appearance of signaling, okay? Faster than light signaling, typically. So, in this model-based approach, essentially, I haven't shown that you can't couple classical gravity and quantum matter. I've just said that one, actually quite natural model leads to inconsistencies. Okay, but this does not entail that all classical quantum models are inconsistent. Good. But okay, so let's think. So now let's take a kind of like foundations, put our foundations hat on, and like what's the type of methodology that we like. Okay, so we'll just use Bell's theorem as a kind of canonical result. So what Bell is doing is, okay, sure, he was thinking about Bohmian mechanics, okay, a particular model, classical model of quantum mechanics. He noticed it had weird properties. Okay, but in Bell's theorem, he actually kind of looks at all possible classical models. Any classical model of quantum theory must be non-local. Okay, and this is what I'm calling a principle-based approach. Okay, he's not looking at a specific model, but he's kind of talking about the principles which generic models must obey. Okay, so this is what I suggest. Principle-based approach is what I suggest could be useful in this context also. So, okay, so instead of constructing specific models of classical quantum couplings, maybe finding they don't work, let's just characterize all consistent classical quantum interactions. What features must they have to be consistent? And that might then help guide us. Okay, and first, I'm just going to give you a very simple example. So it is possible to couple quantum and classical systems together in a consistent manner. It's quite useful, it is, because it's called measuring things. Okay, so I have, in this example, a quantum spin half particle and a classical measuring device, which is a two-level classical system, right? So diagonal, I'm representing it by a diagonal density matrix. Probability 0 of the measurement device being in 0, and probability 1 of being in 1. Okay, no coherence term, it's just diagonal, and my quantum state can have coherences, okay? So generic. And the interaction is, I start in a product state, so my system is in state psi, my measuring device in state 0, and the evolution, with probability alpha squared, they're both in 0, and probability beta squared, they're both in 1. This is like the kind of decohered version of the von Neumann measurement scheme, if you want, okay? Okay, good. It is actually possible to couple quantum things and classical things consistently. Let's look just for intuition to a few features. Oops, okay, a slight lag. So this interaction here is irreversible, okay, or stochastic, probabilistic, and it features back reaction, so information flow from the quantum to the classical. So if I look at the density matrix of the classical system after the interaction, right, it's this mixed state, it depends on the initial quantum state, which is very good. It tells us that when I measure something, I learn information about the quantum system. And just to be clear why here we kind of have consistency, it's a representation which is linear in probabilities. We have like CPTP maps and all this kind of machinery of operational quantum mechanics. When you have like CPTP maps or like stochastic maps for classical systems, you'll never have like violations of like the Heisenberg uncertainty principle or signaling, right? You kind of enforce consistency. So that's, I think, one of the benefits of this operational approach. Okay, so now I've shown that it's if we're trying to characterize all possible classical quantum couplings, there are at least some consistent ones that we're talking about. That's a good thing. Good. So here I'm going to talk about the general case, which is based on this paper. It's joint work with Flaminio Giacomini and John Selby. Okay, so what's the general setup? We have a system S, which is quantum, a system G, which is classical, and they interact, right? That's just the basic thing. So S goes in, G goes in, then have some output states. And we're going to characterize all consistent classical quantum interactions. Okay, note in the paper we do this for like GPTs, so non-classical systems more generally, but for the purpose of this talk, we're looking at quantum systems. Okay, so I've already introduced the notion of like reversible interactions. So I is reversible if there exists another interaction inverse, which is just the identity. So unitary quantum mechanics, if I FL psi by U, oops, I can undo it. Well, okay, that's skip. But unitaries, you can undo them. The next important concept with this information flow or back reaction, right? So if I have two systems, 1 and 2, which interact, okay, we say that information flow from 1 to 2 if the state of system 2 after the interaction depends non-trivially on the state of the first system, right? So in gravity, that's kind of back reaction, right, in a sense. That's what people call it. You can phrase this just in terms of probabilities. There's like signaling from 1 to 2, if you like, the kind of device-independent way of thinking. Okay, I'm going to give a kind of, the proof is actually very simple, so I'm going to give an intuition. I assume S is quantum, G is classical, the interaction is reversible, and there's this back reaction. So first step, I just apply my interaction. So I have two new states where, because of this back reaction, I've extracted some information about system S, right? System G, there's some imprint of the information about S. So i.e. there's a measurement of S, right? I've carried some measurement. So here, this classical information about S, I kind of copy it. I keep a separate copy in another register. Next step I do, it's reversible, so I can undo everything that just happened, right? So I return the two systems to the initial states. So what I've constructed here is a non-disturbing measurement, because the state of the system is returned to its initial state, with information gain, right? Because here, because of this signaling, I got information. There's theorems which tell us that this is impossible. If you extract information about a system, you must disturb it. Not just quantumly, but in general probabilistic theories. That's essentially all the proof is, right? So, to make it look better, you put in a theorem, and you say the following. Okay, so here, essentially, okay, maybe the structure of the theorem is a no-go theorem, because I took a bunch of assumptions and showed they can't hold together. Therefore, at least one must be violated, okay? So assumption 1 is the system S is fully non-classical. I'll explain what fully means in one slide. The interaction is reversible, is the second. 3 was this information flow or back reaction, and 4 was G is classical. Okay, so as a quick aside, there is kind of one fully non-classical is I'm assuming that the system S is not super-selected. Okay, so when you have superselected systems in quantum theory, these are block diagonal matrices, you can extract information reversibly, right? Because you can measure which sector, am I in the top left or bottom right, without disturbing the system to this kind of classical information. So that's the small technicality, which I won't bother with now. Okay, so then now this is what I'm talking about, the principled approach. In any kind of coupling where I have a classical system and a quantum system, okay, so if I assume G is classical, well then either I could reject the first premise. So sorry, if I just assume the gravitational field is classical, I could reject the first premise that the system is quantum, right? I mean, so classical GR and classical systems is fine, that's good, and it's reversible. Otherwise, if I want to hold on to my system being quantum, I could reject reversibility, okay? And number 3, this back reaction is rejecting the influence of matter on gravity, which, yeah, we kind of want to keep, really. So it seems that reversibility is the only kind of thing which we might want to change. Good, so to return to the question of should we quantize gravity, I'm saying that essentially your commitment to reversibility, if you're committed to reversibility, you say physics is fundamentally reversible, quantum field theory is reversible, general relativity is reversible, successive theory must be reversible, then yeah, you have to quantize gravity. Okay, or classicalize matter, which is actually what I said when in this semi-classical approximations you violate the uncertainty principle, is because your quantum matter has inherited classical properties, essentially. Right, so when you have reversible couplings between classical and quantum, essentially it kind of the classicalness can spread to the quantum, or the quantumness can spread to the classical. Anyway, so so historically, okay, so this is now going back to the kind of idea of model building versus principle. It's why are people historically in favor of quantizing gravity? Is because there have been a number. They didn't just like decide this, right? They had lots of debates and arguments, thought experiments, kind of no-go results. So like Feynman and Aharonov have all these types of results. But actually, when you look into a bit more deeply, they all assume quite implicitly, often, reversibility, very implicitly. Okay. So I'm saying that's why sometimes it's good to actually have like kind of clear statements and theorems, no-go theorems that make the assumptions clear, especially in interdisciplinary areas. Okay. So, building models and dividing thought experiments is useful for guidance, but principle-based approaches allow for greater precision and clarity. Okay, so the theorem shows that any classical model must be irreversible. It doesn't show that such a model exists, right? Because when I'm talking about classical quantum couplings in the context of GR, you'd want something like diffeomorphism invariance, at least spatially, for instance, and other properties like this. Okay, so it turns out there is such a model, right? So Jonathan Oppenheim, who gave a talk here, his post-quantum theory of classical gravity, he couples the space-time metric in a spatially diffeomorphic way to quantum field theory in this consistent way, exactly because, so the quantum fields back react on the space-time metric, but in a stochastic way, essentially. Okay, good. So just to go back, kind of the kind of like collective wisdom, right, over the past 60 years. I like it. Milnik has this very nice paper, and he says, at the end, so he studies these couplings in the context of reversibility, and says, though it may be very difficult to quantize gravitation, it's even more difficult not to do it. Okay, which if you have reversibility is true. Okay, so I just want to stress this, right? And so then when you notice this, it offers another way out, which is irreversibility. Okay, I just said this already about this kind of like important to have this interplay between them, especially in these interdisciplinary areas where people don't necessarily share common assumptions. Okay, and just to kind of finish, so what next? In all my discussion about what physics is about, models and principles, we missed the kind of crucial ingredient, which is experiments. Okay, so we've had some talks about this. And yeah, I really think that these gravity-mediated entanglement experiments will actually allow us to adjudicate between, for instance, the kind of model suggested by Jonathan Oppenheim and kind of other approaches which do choose to quantize gravity. I like a lot that Maris said, actually, I mean, modulo background assumptions, right? Like, there's still lots of theoretical work that's being done that needs to be done on these experiments. Yeah, and that was my talk, so thank you.